Hello, everyone. My name is Hanyu Cheng. Thanks for the opportunity to be here. And I'm based in Tyndall Institute in Shanghai, and I visit the University of Sheffield in UK now. And today, I want to talk about two of my recent interesting projects. And the first one is constraining pressure-based dynamical backend models with latest cosmological data. Recent DASI-DR2 result tells us the deviation from the Lambda CDM more than 2 sigma across a different data combination. It hints at the dynamical backend. And specifically, when we use the CAMB plus DASI plus DASI5, it shows 4.2 sigma preference over Lambda CDM. And in our model, we use the different parameterization, which is pressure parameterization, to test that DDE. For this case, we do the Taylor expansion for the pressure P instead of the equation state of C, as you can see in this formula. And P0 is not free parameter in your case because it's related with omega backend 0. And for the first order expansion, we have one free parameter P1, which is equivalent to the omega 1. And for second order expansion, we have two free parameter P1 and P2, corresponding to the omega 1 and omega 2. This pressure parameterization could provide an independent, consistent check. And we use two statistical methods to test our results. One of them is the delta chi-square test, and another one is Bayesian evidence. And this is the formula we use for pressure parameterization. And we do the Taylor expansion for the pressure based on the present day value for the P. And we use a continuity equation. We can get the formula for the energy density of the dipole energy and the equation state of dark energy. This is for the first order expansion. And in this case, we need to notice that when the denominator of the equation of states equal to 0, which means when we approach this scale factor A pole, this equation of states will have the pole here, which means the equation of state will have a divergence. And this corresponding to the energy density cross to 0. And the final result tells us this data doesn't prefer this pole case, so it doesn't bother us in our project. And for the second order model, we have another extra parameter, omega 2, and we also have the equation of the energy density and the equation of states. And this is some illustration plots for the second order case. And here we fix omega 2 and omega backend 0 while varying omega 1. And our model shows the comprehensiveness of the different backend case. We include the quintessence behavior as this curve, and we also have the pure fountain backend case as this curve. And we also include the fountain crossing case in our model and also pole case here. And for our results, the first order expansion results tell us that when we use the CMB only, it gives a rough estimate for every parameter. And if we add CMB plus BAL, it's trending in the right direction to solve it alleviates the H0 and SA tension. And when we add the supernovae data with the CMB and the BO data, it goes back to the Planck result again. And in this case, when we use CMB plus DASI plus DASI5, it gives the strongest preference for the DDE, and it also gives the best delta chi-square value. And the other cosmological parameter remains close to the Planck CDM results. This plot tells us like when we use the CMB plus DASI result, or H0 and the omega m value goes to the right direction to alleviate H0 and SA tension, which is different with the CPL result. For CPL results, when we consider CMB plus BAO, it's worse the Hubble tension. And if we add supernovae data, it pulls H0 and omega m towards Planck value again. And this is for the second order expansion results. In this case, it's all the delta chi-square is negative, which means the data prefer our model better than Lambda CDM. The strongest evidence is given by the CMB plus DASI plus DASI5. It gives more than 4 sigma preference over for the DDE over Lambda CDM. And the Bayesian factor is also positive value. And here, the constraint also shows the very strong negative correlation between omega 1 and omega 2. And this explains the omega 1 and omega 2 always takes an opposite sign here. And we reconstruct the evolution of that energy density, and the blue curve corresponds to the first order model, and the red line corresponds to a second order model. For the first order model, it's a mild change. And for second order model, it shows a non-monotonic behavior. And it has a peak around approximately 0.7 or 0.8. And also reconstruct the equation of state evolution. And also the blue curve corresponding to the first order, red corresponding to the second order, and this green corresponding to the CPL case. And for our first order result, it's always stay in the quintessence region. And for the second order, you can see also the non-monotonic behavior, and it agrees very well in the late universe with CPL. And it also shows the fountain crossing behavior here. And we also reconstruct, we also test the WZWA plot, use this W0WA definition in the present day. And this is for the first order result. And it shows very tight constraint, and it's near Lambda CDM point here. And it shows a very strong WZWA degeneracy. And for the second order parameter space, it's very similar to a CPL case, as you can see here. And it gives the strong evidence for the DDE. And when we compare to the different data combination, we find when we use DASI, it always gives a stronger DDE preference than SDSS. And when we use DASY5, it always gives stronger DDE preference than pat-down plus. And we also compare our model with CPL. For our first order model, all the delta chi-square value are worse than CPL. But for the Bayesian evidence, when we use the dataset without DASI, it shows a positive value, which means data prefer our model more than CPL because we have one less parameter. And when we include the DASI, it prefer the CPL again. And for the second order model, all the absolute value of delta chi-square and their tologency are smaller than 1, which means our second order model is behave similar and indistinguishable with CPL model. This is a summary for the project 1. And for our first model, it's generally consistent with Lambda CDM. And when we use CAMB plus BO data, it could alleviate H0 and SE tension. And for the second order model, it shows non-monotonic behavior in both W and low. And our result shows our late evolution of W agrees well with CPL parameterization across different data sets. It also shows the random crossing behavior and also shows that energy is weakening. And the important thing is CMB, we find CMB and DASI and plus DASI5 always give much stronger preference for the DDE compared to other dataset combination. And the second interesting project I want to talk about is constraining exotic high-Z reionization history with Gaussian process and CMB. This paper is just appeared in the archive today. And during the realization, the intergalactic gas transition from cold and neutral to hot and ionized include many complex mechanisms, such as structure formation, thermodynamics, astrophysical source. And this plot shows how Xe evolved with T. And the ionization includes 3 main CMB signatures. The first one is temperature and isotropy. The second one is polarization. And third one is the KSC effect. In our project, we focus on the polarization signature most. And the key quantity for measuring the ionization is electron Thomson scattering optical depth, tau. And in our project, we also consider the new physics source. Could be dark matter decay, PBH, evaporation, and exotic energy injection. And this plot is from the Planck 2018 paper. It shows how different likelihood constrain the tau. And in this plot, as you can see, as this low E curve, it shows Planck low LE in all likelihood gives the strongest constraint on the residential history compared to other likelihood. So in our project, we mainly use the low LE likelihood. And this is overview of our work. We implement a new flexible GP-based residential scheme in the class code. And this scheme helps us constrain the high redshift residential history. And we first proposed to use high redshift optical depth tau high z posterior to constrain energy injection in the residential history. There are two advantages. First is this model independent reconstruction of XE. And the second is this tau high z posterior offers a tighter constraint on the new physics source compared to the low redshift tau. And our code is public, and we use the low LE likelihood mainly. We use the Gaussian process method in our project. We use RBF kernel for GP method, and this could give us the prediction for every XE value for any redshift z. And we also use a 10 transition between different adaptive bins. Adaptive bins means we take a smaller interval at low redshift range for bins and larger interval at a high redshift range for the bins. This is if it makes our calculation more efficiency and is reliable in the physics, because in the low redshift range, the XE always have a sharply change, and in the high redshift it's always more flat. And we use the 10 transition to connect different bins value. We also include the boundary condition. For posterization, we use the singly ionized XE value, and for the pre-ranization, we set the lower bound for the XE, which is 10 to minus 5. And this is a workflow of our project. First, we need randomly giving the training array, XEZ, and Z. And we use a GP method. This GP method could give back us XE value for any Z for the every bins. And we use a 10 transition to connect each bins. And in the cobaya, we fix all the parameter, other cosmological parameter to the best fit value of Planck 2018 Lambda CDM result. And we give a prior for the every hyperparameter for the GP method to run the MCMC. And this could give us the constraint XE history and also the posterior distribution tau low z and tau high z. And one way to constrain new physics use the tau low z and tau high z posterior. And another way is directly use the Cheng's chi-square value. We give the 95 CL chi-square value, and we can compare this with the different multiple chi-square, and we can also use this way to constrain the new physics, and we check the consistency between these two ways. And this plot shows when we set a different input XE and Z value and the different value for the hyperparameter, it could give us back the different shape for the XE versus Z plot. We want to explore XE versus Z parameter space as flexible as possible. And this is our final result for constraining the XE versus Z history. And in this plot, we extending the redshift range to the 800, very high redshift value. And in the low redshift range, the result is very consistent with the Planck result. And in the high redshift range, you can see there's only upper limits for the XE value. And we can use this upper limit to constrain new physics, which is very interesting. We also define a new parameter ZC, because we want to figure out how can we split the high redshift and low redshift contribution. And we want also test how this tau high z value and tau low z value change when we vary the ZC value. And this tau low z is integration from 0 to ZC, and tau high z is integration for ZC to Zmax. We set Zmax to 800 by hand in our project, and it could set to a higher value pre the recombination. And we find the tau high z and tau low z value is quite stable when we vary the ZC value. And this tau low Z value is quite consistent with a Planck result. And the tau high Z only have an upper limit. And we also give the posterior distribution for tau low Z and tau high Z. You also can see here, even when we vary ZC, the posterior distribution is quite stable. And the tau low Z value is nearly Gaussian distribution, and for the tau high Z, it only have the upper limits. And we can use this method to constrain neophysics. Here we give the one example for irreducible axion decay. Irreducible means if this axion field exists, it will naturally freeze in. And when this axion decay to the high energy photon, the gamma ray, it could ionize the neutral hydrogen, and this could enhance the ionization fraction axis, like this red curve. And the black curve shows the Lambda CDM result. And this will also enhance the tau value. And use our method, we can constrain this tau. And this is a plot for this example. Use our tau high upper limit. We can constrain the parameter for the axion mass MA and the axion photon coupling GA gamma gamma. The yellow curve shows we use the tau high Z to give the constraint. And the red curve shows we use the tau low Z to give the constraint. And we find when we use the tau high Z to give the constraint, it's much better than the tau low Z constraint. The tau low Z result is consistent with the Planck optical depth result. And we also compare our result with the Langhoff paper, the result from Langhoff's paper. They use a totally different method to constrain tau, but we get a very similar result compared to them. They derive their constraint from freezing abundance. And we also compare the tau high Z result with a chi-square analysis, which is shown as a white curve here. And we find them agrees well. And our tau high Z result is a little conservative compared to the chi-square analysis, which means our tau high Z posterior constraint is quite reliable. And this is the conclusion. In this project, we propose a model-independent approach. And we run the MC-MC analysis with around 20 GP parameter. And we mainly use the Planck law LEE only single likelihood. And we introduce a new derived parameter, tau high Z, which calculates the high Z contribution to CMB optical depths. And this could extend the existing Planck analysis to high redshift range. And we also verify our result via chi-square analysis to show our result is reliable. And we can use this model-independent posterior to testing any energy injection model. And we show one application for this method is decaying irreducible axion dark matter constraint. And for the other example, string axion constraint, please see Ziwen's poster for more detail. And we think it's very important method because it's offer a new and clean and general way to constrain new physics using tau high Z posterior. And we publish our code for the modified class code. And we will update it with latest chains and other related Python code. Thanks. That's all.
Thank you very, very much for your talk. So we'll have time for questions. Here.
Thanks for a nice talk. Regarding the first part of your talk, did you check if your results are robust under including higher order terms in the Taylor expansion?
Oh, okay. Yes, this is we think we can always expand to the higher order for the pressure. And I can show this plot. This plot is a Planck 2018 result. They test a different model with different number of free parameter in the expansion. And also they test the chi-square value with introduce a more free parameter. And in our case, we test the first order expansion and second order expansion, and we find the second expansion that chi-square value is close to a CPL value. And we think like our delta chi-square could not be improved more compared to this, because it's very equivalent to the CPL value, which is considered the most the best chi-square result. And we don't want to add more parameter, because add more parameter could worsen the Bayesian evidence.
Yeah, but I was also asking because there is the possibility that the evidence for, say, phantom dark matter diminishes as you include more parameters, and that might be interesting from a theoretical perspective. But
yes, I agree.
Yeah.
This could be considered later.
Yeah. Okay, thank you.
Yeah.
Any other question or comment?
I want to know if your result is not so, so well with the Langhoff result, why we choose to use your tau high Z constraint?
Because this result is independent with their result, with Langhoff result. In Langhoff result, they mainly use the temperature and isotropy to give the constraint for this axial model, and they give this result. And in our result, we mainly use a tau high Z posterior to give the constraint, which is rely on the CAMB polarization dataset. And in this case, our model gives the very similar result as them. And our model is model independent. Our method is model independent, and it could be applied to like other new physics model. Also, we think our model is more robust and general.
Okay, thanks.
Yeah.
Let's thank the speaker again.
Thank you.